Okay, we're good.
All
right, so series for E. So here's the problem with this integral again. There's no fundamental antiderivative, so I can't use the fundamental theorem of calculus.
Super problematic.
So that's a problem. However, we know Taylor series. And we know the Taylor series for e to the x is equal to 1 plus x squared over 2 plus, what's next?
X cubed over 3 exclamation points.
Yes, so 3 factorial, okay, and so on. So we're getting closer. So next we need to know what is the power series for e to the x squared. Or we can say e to the t squared.
I was right.
We just do a substitution. We replace x with t squared. So then we'll get 1 plus t squared plus t squared squared.
So fancy. I like this.
I think these are just fun. This just
makes it so easy. It's simple.
When I took calculus, I thought this was the funnest quarter of calculus.
Well, that just seems really easy.
Yeah.
I'm not even going to write that down.
I agree. This is so far my favorite.
Yeah, I know. Like, Calc 1 was, challenging. Calc 2 was just...
Wait, is it your favorite because it's easy, or is it your favorite because...
It's fun.
It's
and
fun
if you understand it and you finally understand why you've actually done any math ever.
I know.
There's some parts of this I don't find easy, but it allows me to solve problems that I couldn't solve otherwise. In particular, I like a field called differential equations. And I liked power series even more when I discovered you could use them to solve differential equations. Classic problem where power series come up with differential equations is some wave equations. Like what happens when you beat a drum?
Oh yeah, you told.
What happens if you're holding a metal rod and somebody whacks it?
So do you
Feel that vibration?
So does calculus 3 come up in physics often then?
It does anywhere you have series solutions to things, or when you want to change your coordinate system, which we're going to do next. Change coordinate systems.
Oh, okay.
All right, so I think we're ready to integrate, right? We just want to integrate this.
Oh my
which means
goodness.
we want to integrate that. And we're going to then have to also evaluate boundaries.
It's just fantastic. There are all these little tricks.
Okay, so not too bad. Let's do it. We're going to have an arbitrary constant, so I'm going to put that in on this side. And then I have the antiderivative of 1.
Which is obviously just x.
Which is x.
I mean t.
T, yeah. See, we're not ready for x yet.
Yeah, mixed variables now.
And then we're going to get a t cubed.
Over 4 times 1/3 if you're basically.
Yeah. 4 times 1/3. They're both lovely. And then you're going to have, what, t to the 5th?
T to the 5th.
Times 1/5, but it's still over 2, so that makes it 1/10.
Yeah, I'm going to leave it as the 5 times 2, just so I might see a pattern.
Oh.
So that's another thing. You know how we were looking for a pattern with the square root? It helped me to find a pattern by not multiplying things together, to see where those numbers came from.
Yeah.
And I was hoping that would help me generate a pattern. And sometimes it does. What's next? T to the 7th?
T to the 7th over 8 times 3 factorial.
Ooh.
Right?
Over 7.
Oh, 7.
8 times 3 factorial. That's the power to match.
Right.
And then it's just going to keep going, and I have to evaluate from 0 to x.
That was so easy.
Okay, so then we plug in our x's and we plug in our zeros. So that is going to give me.
Except for the
Except
yeah,
C.
C.
So
Which
I
C is
have
the 0 and
C the constant anyway.
C is 0.
C
C is
plus.
necessarily 0.
Not necessarily. Some problems it's not 0. It's just the ones I picked so far it has been.
This could be like 17.
Well, I mean, like if you're 0 on there, it could be 0.
So let's see. C
It's
plus.
a constant.
Where was I? X
8
plus
2
x cubed over
1
3.
Yep.
X to the
1,
5th
not 0.
over 5 times 2. X to the 7th over 7 times 3 factorial. And I could actually call that 2 factorial. I could put a times 1 factorial there.
Well, why would you do that?
I could down here put a 1 times 0 factorial there,
Oh my gracious.
Which is just normal.
right? So I'm kind of generating a pattern,
Oh, yeah, I see it.
right? Maybe. Now I'm not done, right? Because this keeps going. And then I have to subtract when I plug in my lower bound. My lower bound is what? 0? So I'm going to have C plus a whole bunch of zeros. And here's something cool. What happens to C in this case?
It cancels
It
out.
cancels out.
Oh,
So now we have
snap.
the integral from 0 to x of e to the t squared dt. It has the following power series. X plus x cubed over 3 factorial plus x to the 5th 5 times 2. And that is not a 3 factorial, it's just a 3.
Let's start writing this thing.
Yeah, I know.
Plus x to the 7th over 7 times 3 factorial plus yada yada yada. Anybody want to take a stab at the nth term for this?
Is the x
So-
to 2n minus this?
Okay, so let's figure out where we're going to start counting. If I count according to up here, like with the 0 factorial, do I want to start counting at 1 or do I want to start counting at 0 there? That's important. That'll determine how we use and.
1.
You're thinking 1? Because I was thinking 0, 1, 2, 3.
I think you should start counting at 0.
But you can count at 1. It doesn't matter. You just have to adjust your numbers to go it. So I would count at 0.
Okay.
And
So when making the series, the nth series part,
Yeah.
is it just practice and playing around?
It is practice and playing around. And I, as much as I've done, I'm not at the point where I can just write it down and be sure I'm right without checking. You just,
Is practice.
it's just, yeah. Okay, so let me see. What do we got?
that one.
Yes.
So I'm going to have an n factorial on the bottom if I start counting at 0.
That's what I got. That's where I started.
And then I have odd number related to that. So I think it's going to be 2n plus 1.
Yeah, or I got the
Okay, so let me just check. So this is 0, 1, 2. So for the second, for n equals 2 right here, 2 times 2 is 4 plus 1 is 5.
Oh,
Yeah, so it looks like it's going to be 2n plus 1 if we start counting at 0. If you started counting at 1,
yeah.
2n minus 1 would work.
Okay.
Yeah. And then my numerator is just x to the 2n plus 1. Hey, we got a formula for it. That's kind of cool.
Super snazzy.
Right? So we can actually state that would be the sigma notation for it. Right? So we could say this integral is equal to the sum as n goes from 1 to infinity of x to the 2n plus 1 over 2n plus 1 times n factorial. Next question. What is the radius of convergence of this black series? Let's figure that out.
Okay. So I recommend that we do the ratiotic test.
Ratiotic test is x.
That is what I recommend. Let me solve this. Right. Just start. This is such a great review.
So this one problem is going to review everything, pretty much, that we've covered since section 7.
Oh, good.
So
Snazzy.
we're going to use the ratio test. That's a good one. So that means I have to take a look at what is a sub n plus 1 over a sub n, and that's in absolute value. And then once we clean that up, we'll take its limit.
Plus 1 plus 1. dot.
Get it today.
Laura, you're so close every time.
And this one's in the tail is actually fun.
Let me take the limit, so I always forget to write that.
Wait, why is that 2n+?
Because you distribute the two here.
And then you add it, I want
And
it.
so
Oh.
this would be 2n plus 2, then plus 1.
Right.
Excuse me, 2n
That
plus
was
3.
silly. Got it.
So that's why I wrote it down this way first, to just slow down and think about it.
Do you even math?
You said that.
Did you just say you said that,
I
Courtney?
said, you just said that.
I did say that.
I see what just happened. Okay. Slight thinking.
Okay, so I think this is what I'm left with after I clean stuff up. X squared times 2n plus 1 in the top, 2n plus 3 times n plus 1 on the bottom.
Uh-huh.
I love it when you clean stuff up.
All right, so next we have to take the limit of that sucker.
Distribute it.
Yay! Limit of that.
That's what I was enjoying. With the times taking limits.
I was going to drop that.
I get 0.
Yeah,
Why do I get 0?
Did you
because
distribute
it's
the bottom
to
though?
distribute the, it's
So
the n squared on the bottom.
the x-
and then
The
you have,
absolute
like,
value of
one
x squared, yeah. So the absolute value of x squared is x squared, and that has nothing to do with n, so that just comes out of the limit.
Yeah.
So then all I have to do is consider now what is the limit as n increases of 2n plus 1 over, in the bottom I have 2n plus 3 times n plus 1, which you could multiply that out if you want, and then you'll get 2n squared plus 5n plus 3. And the degree at the bottom is greater than the degree at the top, so it overpowers as n goes to infinity, so this goes to 0, because the bottom goes faster.
That was the brain power I used.
If you weren't
And
sure
then
about
plus
that,
one.
you could divide everything by n squared. That was our trick for that.
That's,
And you'd still get
Yeah, I
0.
was so good.
Yeah.
It's
So-
just to
yeah.
show it.
So if you didn't remember this from Calc 1 or college algebra, then you could divide by everything by n squared. And you'll still get to 0.
I do it.
But my assumption is on rational limits that you guys know the rules like I do.
That's less than.
So can we
Yeah,
assume
plus
you
one.
know that?
Yes.
Good.
okay.
I don't want you, like trick you with any magic that I do on my
I'm
paper.
probably
Right.
so
Well,
good.
sometimes you have to follow intuition, but intuition isn't always right.
My
I
magic.
just don't like
My-
how
my
it's
magic
like,
man.
I just
My
don't
magic
like how
man.
you would
How
spend
it will.
2 hours writing out explanations, which is what happens.
Oh, I
to
don't
me.
mind
I
at
spent-
all.
I spent forever on it. I'm like, okay,
Because
I'll
I
give you a
feel better
detailed
about
essay
it.
on every single problem.
Hey,
What's the
did you
radius?
see my explanation? My explanation was pretty broad.
Well, I
The
think
drawing
that we should, I know that it's between -1 and then +1. No, that's false.
What does the ratio test say after you take the limit? How do you draw a conclusion from the limit?
It converges or diverges.
If
the limit is less than 1,
the limit is
then
less
it
than 1,
converges.
then the ratio test says it converges.
Right.
Now, are there any conditions on what x values that this is true for?
No,
Where
it's
did
all
x go?
numbers.
Yeah, x disappeared, so that means it's true
The
for all real
radius is
numbers.
infinity.
So the radius
Reals.
is infinite.
The radius.
We have convergence, we have
Nice.
absolute convergence for all real numbers.
I love it.
Which is nice because I don't have to check the endpoints.
Oh yeah.
Are you sure you don't have to check infinite and negative infinite?
Yeah. Hard
That
plug
would-
in.
I would
unless-
cry.
I wouldn't. I don't really think it's that bad.
I think that would be bad.
I think that
How
I
would
would
you do
rather
that?
check the endpoints all day long than ever have to have these two things.
Okay, yeah. I have to agree.
Let's graph this and see what it looks like. I'm curious.
After a problem.
Feel like you know what it looks like.
There we go. We're going to graph that. And I'm going to do it on GeoGebra.
Why is the calculator?
I think I forgot it.
So whether using GeoGebra or the TI, it's a sum sequence command, right?
Yeah.
Oh, howdy, Zach.
Oh, no, no.
Go home, Zach.
Be nice.
I thought you were talking to me for a
Okay,
second.
so
I was like,
I'm going to sum
Don't assume that I'm
sequence my expression is x raised to the power 2n minus 1
Wait, that's
No, plus one.
almost like exact.
plus 1
I don't need you. Okay.
You don't have to.
divided by
I ate 3
parentheses.
before I eat.
Parentheses.
And
You're going to need
some
a
ice
double parentheses in the bottom.
Was it at school or something?
No, it's all at my house.
You guys graphing this?
My computer's frozen. Like,
Oh.
it's not.
Your computer?
And I just pulled mine out from my
Practically
backpack
my
like 2 seconds ago.
Times
Oh, this
n
is what happened.
factorial.
So there was Mother's Day,
First
my brother's birthday,
Oh,
and I had some dessert baked cookies.
What in the hell have you done?
Variables n starting at 0. I'm going to go 10 terms.
Okay.
4.
Okay.
Ooh, interesting.
It looks like a cube.
It does look a little like a cubic, except it grows wicked fast.
Nice. Solid. Okay, so this is what's gonna happen. Where is?
Wait, how did you get that down?
How do I even do this? I like forgot.
How do you get the downward angle?
There?
Mhm.
Good.
Sum.
What? It just did.
Sequence.
Oh wait, is this still that ET squared one?
Wait, how do you get sequence? Oh, there it is.
So we are graphing
Oh, yeah.
these terms right here.
Well, that makes sense why.
Yeah, odd powers.
But we actually put in the x to the 2n plus 1.
Yeah. So and then you want to be careful. You'll have to put parentheses around the whole denominator on the calculator,
Yeah.
unless you have that pretty print math going on. It doesn't work there. I don't know if it works in the sum sequence.
So wait, we have to put this in just a part?
We're doing the sum.
Sum. Oh, doing the sum.
Yeah. I wanted you to graph it. So my claim is that the graph looks like this.
Whoa. Oh, I have it written down.
And I only have the first 10 terms, so for fun, I'm just going to put like, the next 20 terms up to see what they look like too. And they sit right on top, so maybe I should change the scale to see if they diverge.
How far did I move it?
So this is a rapidly growing function. Oh, you can see they start to separate out after about 2.5-ish. You can start to see a separation.
That's pretty crazy.
So that's the 10th partial sum versus the 20th partial sum.
How much difference?
What's our radius again?
Infinite.
Yeah, it's infinite. Now we can't graph the real function because it doesn't exist as anything but an integral or power series. Just for fun, I'm going to ask Wolfram Alpha what it thinks. Oops, that's not what I want.
Okay, so that's 10.
There. Okay, there we go. And so I'm going to give it the original one. I'm going to give it integral of e raised to the power. Oh, look at that. No, not 2x. I want x squared. This one right here. And, ooh, it gave me something here. It's calling it the Urphy function. Urphy.
That's fun.
Yeah.
It's the imaginary error function. There's another one called the error function, and you get the error function if you make the x squared negative. And that gives you the Urph function.
Wait, why is this one not imaginary? The other one is?
I'll show you. So if I replace x squared with a negative x squared, that will alternate the series. So I'm just going to go adjust this first one to alternate. So then I would just need I started at 0, so I'll need a -1 raised to the n. And that's going to give me a very, what?
You.
Didn't do what I wanted.
Nothing.
Did I type it wrong? Oh, it didn't even
I didn't even
do it. It's weird. Parentheses. Oh, maybe I did 1 to the end by mistake. -1, there we go. Raised to the n. Apply, and it should, it's a little better. And then I want to say, okay, turn this one off, and it should look different by the origin. It's not consistent, right? What am I doing wrong? Okay, so my assumption. I did something wrong. Okay, let's figure that one out then. I'm curious. Let's start over with the integral from 0 to x of e to the -t² dt. So see if you can come up with a power series for that based on what we just did. Somewhere. I already see it.
Oh, wait. Oh. I understand. Okay.
Looks like it's just alternating.
It does.
That's what it looks like to me too.
So I typed something wrong in GeoGebra because that's not the graph I was expecting. So this is then the sum as n goes from 0
Oh my
to
gosh,
infinity.
it's so much faster.
That's because I've done it before.
Didn't we have that plain faulty?
Wait, is that like what?
There's a term called, remember you guys, arm players equals.
Oh, what is it?
Faulty.
Oh, that makes sense.
Arm faulty.
I was thinking like
Guys,
variable faulty.
faulty.
So it's n equals 2, it's positive, n equals 3, it's negative. That looks right. Okay, so what did I do wrong in GeoGebra? Because it's not the right graph.
I don't know.
Really?
Wait, what did it else?
Yep.
Oh, I'm thinking now.
It is. At first you're like, all of them are negative, and
Yeah.
then you're like, it's negative t, you have to put it on the axis, so if you square negative, it becomes positive. I did it like that.
Yeah, so like this term right here, if I square
That's
negative t squared, it's going to be positive 2.
That was just T.
Oh, just listen.
If I square negative t squared, negative times a negative is going to be a positive.
See, I tried plugging it just all into the interval or the E,
Here?
just to ET squared. So I just did instead of E to the X.
Yeah, you're going to plug negative t squared in for e to the x.
Yeah, but I didn't use E to the X. I used
Okay.
E T squared.
Okay. All right. Yeah, so that would be.
That's it.
All right. So,
Trying
why
to
did
skip a step.
GeoGebra not graph it right? What I type looks good.
You need any extra parentheses to break things apart?
I think so.
Problematic.
It shouldn't need any extra parentheses. I could put it on the numerator, but that shouldn't be mad. I need -1 to the n, right? Are we in agreement on that?
Yeah.
Interesting. Well, I guess that's what it does look like. I must be thinking of a different
The one
function.
is on the 14th.
Oh, right.
Openly.
That is what it looks like.
But I would just.
Okay, I'm good now.
Wait, yeah, isn't that right?
I was thinking of the graph of e to the negative, before the integral, the graph of e to the negative x. That looks totally different. So let me show you that here quick. E raised to the power of negative x squared. I was confusing the original function with its integral. So this is what I was hoping to see. But if I integrate that from 0 to x, I will get this increasing area curve. So this is the area curve that we graph for the power series.
Oh.
So for example, let's just double check. If I ask GeoGebra to find the integral,
We're going to say finds integrals for you too.
well, sort of. It finds them numerically. Sometimes it can find them directly. Watch. So if I just say find me the integral of function h, which is what we were doing, and I hit enter, it's going to think, and it's going to say it's the error function.
Oh my goodness, that is so fancy.
Right? And if you've never heard of the error function, you're like, what the error function? I don't know what that is. So I can also integrate numerically. So if I say, GeoGebra, tell me what the integral of the function between two numbers is. Like, I want to know what the integral of h is from 0 to, let's go to 0.5. Because that's on my screen. So the GeoGebra says that area is about 0.46. If I then say, okay, if I take my power series f, what is the value of f at 0.5? That power function should be my area function, because it's the antiderivative. So f of 0.5 should be 0.46. The same as, can you see it there? The same as the integral.
That's pretty cool.
How do we compute numerical integrals of functions that don't have an antiderivative? Power series is one way to do that. Without power series or some other technique, we're out of luck. Can't do it. Okay? So, I don't know what method GeoGebra uses. I can look it up, but it could be a power series method that's programmed into it. But I doubt it. There are more sophisticated methods than that.
Ways that we don't know.
Ways that I don't know.
Oh.
So much math I don't know. It's astounding. Okay. Next step. We want to be able to approximate
Wait, is this chapter 11?
No, this is still one more question for chapter 10.
Okay, I
We'll do
just want to
chapter
make
11.
sure, because when we start chapter 11, I start a new page.
Yeah,
We
me
want
too.
to approximate
I start a new whole section.
this integral. And let's go with e to the negative x squared since we have that.
Approximate the world. I don't know. Things are just coming out of my mouth. I don't really know what.
It's okay. It's been 11 days, 22.
No, it's not one of those days. I'm just tired. I stayed up too late.
So we're going to try and approximate this integral as a function. So this is some function. GeoGebra is calling it f of x right now. So I want to be able to approximate f of x to the nearest hundredth.
What?
Watching TV.
Oh, I was too.
So my interpretation of the nearest hundredth is I want 2 decimal places of accuracy.
That's what I was thinking it was.
Okay. So that means I want my error to be less than or equal to 1/1000. Okay.
But
Now, so what I have to figure out is what x values can I use to be within that range? Because at some point, I'm going to separate because I've only done, 10 of them or so. Okay. So, by the way, with this, I'm going to use my 10th Taylor polynomial.
oh wow.
What? How do you know to go to 10? Just
Because that's what I just told GeoGebra to do. I just picked 10.
oh, you just pick 10.
Yeah. So
Okay.
here's the problem. We have 2, as far as approximating with the Taylor series, we have 2 unknowns. We have the x values that we're playing with, and we have how far out we add terms.
Okay.
Just telling me what the error is doesn't help me find what both x and n could be.
Okay.
I have to decide on one or the other. So either with this error, I could say I only care about x's between 0 and 1,
All right.
or I can say I'm just going to stop n at 10. Where does Remember I said I printed your take-home test, but I couldn't find it.
Did you find them?
Well, I gave it to you earlier, but this is the other copy that I tried to print like an hour ago,
Oh.
or 2 hours ago or something. Okay, anyway.
Well.
So just knowing the error doesn't help me fix x and n.
Okay.
So if somebody gives me the error, then I have to decide either what x values do I want to work with, in which case I can use those 2 to find n, or what n am I going to use, and then I can use n in the error to find x.
Let's use n in the air.
That's what we're going to do. We're going to use n in the error. So I'm just going to say n is 10 here.
Yeah.
So now we have to figure out what intervals on the x-axis can we give good approximations for. By good approximation, I mean to the nearest hundredth.
Okay.
So then we have to take a look at Taylor's remainder theorem. And Taylor's remainder theorem says,
Wasn't just there. I liked it there. I understood it.
it's pretty nice.
I currently don't remember what it is, but I understood it when we learned it.
Just gonna make sure I get that heavy.
I'll learn it
I hope so.
eventually.
Taylor's remainder theorem says that the nth remainder, the absolute value, has to be less than or equal to, you're going to have some maximum related to the nth derivative,
Yep.
times x minus your center to the n plus 1 divided by n plus 1 factorial.
Yep. That's what it is.
What is that? Okay, so
Is your,
for this problem, I probably shouldn't have picked 10. Oh well.
We choose 2 instead.
2 would be better, but we're gonna
10.
we're gonna
I
try
like
and do
it
10.
too.
Okay. So the m here is related to the maximum of the 10th derivative, or in this case, the next derivative, which is going to be the 11th derivative
Here's our handy dandy
of my
something
function.
choose something.
Why would you do such a thing, Mary?
I know.
I
that's-
feel did we do that for 10, Mary?
What's that?
Does something choose something, but
Not
not
the combinations.
Yeah. Can you read it?
So the nth derivative, the 11th derivative is what I have to consider here. Now that's a wee bit of a problem, not too much. My original function was 0 to x of e to the
Negative p squared.
negative t squared.
Why didn't you write that in Roman numerals? Now it looks like that's the second word.
Yeah.
Okay. Parentheses. There we go.
Okay.
T squared. Now the first derivative of this with respect to x is just e to the negative x squared. And then let's see. The chain rule applies here. So then I'm going to have a times negative 2x. No, that's a lie. Chain rule doesn't apply.
We could just go to, 2 because then you'd only have to go to 3.
And so then I have to take a derivative of that, and a derivative of that, and so on. So, to speed up time, I'm going to see if Wolfram alpha can do a 10th derivative. If not, then we'll jump to the second.
Solid choice.
Yeah.
All right.
Yeah.
So then what I want to do is, let's see, can I do
Yeah, it's like easily. We should go to bed and not watch TV.
No.
e raised to the negative x squared? Let's see if Wolfram alpha understands what I'm talking about.
So why did we decide to get the negative x squared version?
Wait, like your potluck into the season?
Don't
Don't tell me I seem like
I know, I just decided I want to talk about the error function instead of the
I know.
imaginary error function.
Alright.
No good reason. Let's see, does it understand that this is the 10th derivative?
Awesome sauce.
Come on, come on, come on. Interpreting as the 10th derivative, maybe. It interpreted it as something else. Ooh. What? Oh, it took it as the part. Oh. Huh. Weird.
Oh.
Huh.
Mm.
Not what I was hoping for. Let's try something else. Oh. Okay, it says try typing it this way.
You know, it can interpret words too. You might just be able to say.
I might just be able to say 10th derivative. Try.
So my graduation announcements are finally almost all set out.
Okay. Yeah, just let me know what they are and I'll come and I'd love to have you there.
Ah.
There's gonna be great food at both parties. Like, there's gonna be enough food. I'm pretty sure we could feed a billion people. Maybe not a billion, but a lot.
Food was fun. It was good. What if somebody actually made awesome sauce?
Oh.
I make awesome sauce.
Ooh, look at that. Holy
It is
shit.
awesome.
Okay, check this sucker out.
Oh,
Is that really
crap.
So the 10th derivative of e to the x squared is the 11th derivative of the integral of e to the negative x squared. So, and that's its derivative there.
Wow.
So we took a derivative of the.
That is intense.
No,
So should we write that down then?
No, don't even bother writing that down.
Okay, I am.
All right. So
Right.
let's see if we can
Wait,
make
what
use
is
of that.
that?
It's the 10th derivative of the integral of e to the negative x squared.
Which is the 11th derivative.
How did I get?
It's not, actually, you could do this in an hour by hand. It's not that bad.
How did
But I
In
just,
an hour
No.
by hand.
I'm
yeah,
not
you
sure.
could do that in an hour by hand, yeah.
It's not that bad.
So it's
In
the
an
11th
hour.
derivative of our integral here. Okay. So what does Taylor's theorem say? Taylor's theorem says I have to find a maximum of this function that I have to, that's what m is.
So we're probably
Question?
going to be this hard on.
No, this is wicked hard. No, I didn't make up this problem ahead of time. I
Because
should've-
I was going to say this is a flashback from
Calc 2.
Calc 2 and Calc 1.
Oh, Calc 1 wasn't that bad.
Okay.
One take-home test.
That was bad.
I would have
Bad.
aced that test. I don't know what I'm talking about.
So it looks like that's
That's
10,000,
bitter when it comes to
20,000.
that test.
It looks like a maximum on this thing is about 25,000.
I would have aced it.
It's about what?
25,000.
25,000.
Wow.
I would have aced it had I turned that second page in that last page.
One of the problems.
Okay, so.
Let's jump down to the second derivative. Wait, are you recording this?
Yeah.
Where's your mic?
I forgot to plug it in, so I'm using this mic today.
Oh, okay.
It can hear everything you're whispering.
Everything.
Taco Bell.
Okay, so we're gonna lower our standard here, and we're gonna make that right there T2.
Yay!
Yay!
Should have listened to me a long time ago.
I should have listened to you a long time.
Good job, Courtney. Way to convince the teacher.
Oh!
Or actually, no. Do we want T2 or T3? We want
What about T3?
T3.
Oh, fine. Make that a 3. It's a huge 3 on my paper now. That's okay.
Okay. So lowering our standard, or raising our standard just a touch. We're gonna go with 3. Okay, that makes it a little better. So now I have to consider the So this is the first derivative. What's the second derivative of e to the negative x squared?
I believe that you have to use the fancy handy dandy chain rule, and then it would be negative 2x times e to the negative x squared.
Okay,
Okay.
and m is always related to the derivative
That's
that's just one higher than the one you're going, right?
Yes.
Okay.
Yeah, one higher than the derivative. So we went to the third, so we need the fourth, so I'm going to ask Wolfram Alpha for the fourth.
We're multiplying it.
We can, well, you have the chain, now you have the product rule and the chain rule.
Oh, because there's an x. I don't want to do that. Yeah, I agree. Use Wolfram. Just keep going.
Yeah, I punch words into that more than I actually punch problems.
Yeah,
It's so
I
smart.
know.
It's so smart.
It is.
I was like, hey guys, after
Okay.
test, we should
Do that again.
That was for when we passed the whole class, not this.
Okay, what do you think? There it
one
is.
test.
why not look for more excuses to do a good day?
So if we plug in 0 here, if we plug in 0 here, what value are we going to get out of the fourth derivative?
Like 12.
12. Excellent. Yes, we'll get exactly 12.
Good one.
So 12 is our max.
Well,
Okay.
and it's probably, oh wait, I want to write that down.
Because it drops after that.
E to the negative x squared times 4x to the fourth minus 12x.
That's the third,
Plus
fourth
trace.
third
This
derivative.
is the fourth derivative.
Fourth derivative. So,
Oh, I guess that's one more than I need.
well,
But that's okay.
but isn't that what
'Cause-
m is?
Well, I
Well-
thought you were taking the
I
derivative
thought-
of the integral.
Yeah, the derivative of the integral knocks that derivative down one. So I really should have done the third derivative.
I thought you were starting at the third. Oh, we started at n equals 3.
So what I just did there is I took the derivative of e to the x squared, e to the negative x squared. That is the first derivative. So that means I only have 3 more derivatives to go. So what I should have done is the third derivative. So one more time.
How exactly is m related though?
And this is the max.
M is the maximum of that derivative.
And
Whatever
so,
you can estimate it as. Sometimes we can nail it, like
So
12.
instead of T3, we took T4. And then it was just the highest number that was in there?
Yep.
Okay. So I thought that.
So the highest number in here appears to be about 4 on this one.
Oh, are we only going to the second now?
So e to the negative x squared is the first derivative. I took 3 more derivatives, which gives me the fourth derivative of my integral.
Which means you're starting at the second derivative. When we change the
Wait, so that was the fifth derivative.
You have to go one more.
So this is the fourth.
Well, we
derivative?
started on the third. Okay, so ready? Let's back up and double check this.
We're all
Changing.
We are going to T3, right?
Yeah.
That means that the remainder theorem says you have to look at the next term in the sequence,
You need the fourth one.
the fourth one,
Yeah, which
But-
we did.
which means I need 4 derivatives.
Yeah.
Okay, now, the first derivative is e to the negative x squared.
Yeah.
I asked Wolfram Alpha to take 3 more derivatives of that,
Oh.
which gives me 4 derivatives altogether.
Okay.
And according
That's why I
to
did 3.
the graph here, the fourth derivative has a maximum of about 4.
Okay.
So that's our m.
How did you meet?
M is 4 here. So I'm going to steal this into my notebook.
M equals quattro. I guess MA equally no, yeah. I don't know.
Wait, did you
Okay.
just need that maximum so that you could solve this problem? That's all you need out of that? The only reason you wanted that?
Yeah.
I had to do all that work to estimate m to be 4.
Oh my gracious, golly gee.
Okay.
Sounds so
So
silly.
now applying, it's just complex stuff.
I know.
So the remainder theorem says that the nth remainder, in our case, we want the third remainder. Of x is going to be less than or equal to, we have a 4 times x to the 4th power over, and again, these 4s are independent of each other. This just happened to be 4. This is 4 because it's 1 greater than that.
I knew that.
Over
Let's
4
say,
factorial.
let's say, where do you go?
Wait, wouldn't it be?
A is the center. Center is 0
plus-
here.
Oh, wait, never mind, it wouldn't. Never mind, I lied. Don't even listen to what
Okay.
Casey's saying.
And we want that to be less than or equal to 0.001. Now we're finally at a point where we can solve that inequality.
Yay,
Go
let's do
for
it.
All right, what do we get?
Oh, please.
Go Paisley, go Paisley.
Oh my goodness, I like that. I'm all about it.
Oh, no.
It's just because I liked it.
Okay, so I need the 4th root of 0.006. Is that what you guys get?
I think you're a little ahead of us.
Oh, sorry.
No, he's right on 4th root, 006.
Yeah, that's what I got.
Wow. You got there before you
I
did.
love it.
Booyah.
So this is not a competition.
It is a competition. Don't ever let yourself
Okay.
say that it's not a competition.
No.
Which I get to be about 0.278. I'll go 3 decimal places on
That's
that.
what my brain calculator said too. Just kidding.
Now, do we want to round that up or down in general?
Down.
Always round down.
Down, of course.
0.278. So this is about 0.278. So what I found is that if I need to evaluate the integral from 0 to x of e to the negative x squared, or t squared, dt, and for an approximation, I'm saying it's equal to x minus x cubed over 3, that as long as x in absolute value is less than or equal to, was it 0.278, then my error will be less than or equal to 0.001. That I'll be within 100th of the actual answer is what we just discovered here.
Yay.
Should we test that?
No.
Of course we are going to test it.
No, we did a good job.
So my original function is called the ERF. So we're going to calculate the ERF of like 0.2. And we're going to compare that to 0.2 minus 0.2 cubed over 3. And we should find that they're within 100th of each other.
Hey, is there any error button on the calculator?
What's that? No, our calculators do not have an error function. You could do it. However, you could numerically integrate on the calculator. Let's see if how close that comes to it. So to numerically integrate, you go to what, the math menu maybe? Maybe it's in the first part. I think is it the FN int?
Yes, it is. It's round
Okay.
9.
Oh, check that out! Look at that. So I want to go from
I definitely
0
spent a lot less.
to
I now have that
0.2.
option-ish.
On your,
And then here, I have e to the power negative, and here they're going to want an x squared, oops, dx. Did I get that right?
Exactly right.
So according to the calculator, the error function of 0.2 is 0.197.
That's not.
what?
Well, no, we haven't plugged in 0.2 in anything.
Oh,
yet.
right. Sorry.
Yeah, so I picked 0.2 because it's inside my interval. My interval says I can go from negative 0.278 to positive 0.278.
So 0.2 is a solid choice. Okay.
So 0.2 seemed like a good choice. It's kind of near the edge, but not too near the edge. And then if I compare that to 0.2 minus, parentheses, I guess I didn't parentheses, 0.2 cubed divided by 3. Did I get the divide by 3 right?
3 factorial, isn't it?
I think it's just 3.
Then yeah.
It's just 3.
Because it was the integral.
And how was this?
There's more.
More stuff? Where did you
Hey, Bob.
find these?
On the printers.
In down the hallway? Or the one out here?
That was here.
Where were the other ones? Where were the other ones?
There.
The one you gave me earlier?
Okay.
Oh, okay. Okay, apparently I don't know what term I'm coming to. All right, divided by 3, and we get 0.197. Yeah, so we got 2 decimal places of accuracy in there, which is what we were hoping for.
I'm alright with that.
Looks like you got 4.
If I don't round the original one, I was hoping for 2, I got 3. And usually you get a little closer than what you think. I'm going to ask Wolfram Alpha about this too,
So you use 0.2 because it was 0.278, right?
because it's within the interval, yeah.
Okay.
So if I tried 0.3, I might not be close enough.
You could do 0.21 and it'd be fine. Or
I could even do 0.27, 2.77,
It just can't be
0.277.
bigger.
It just can't be bigger. You're not guaranteed to be close enough if you're bigger. So if I just asked Wolfram Alpha, what is the ERF of 0.2? Now this function has a name. Do all integrals that don't have fundamental antiderivatives have names?
No.
Only some of them do.
We probably don't even know about
Why
all
does
of
it
them.
have a name? And
Listen.
what's it used for?
The error function has a lot of uses in statistics in particular,
Oh, it's not.
and it is related to normal distributions, among other things. Many other things.
So
Ooh, listen. Wolfram Alpha thinks the actual answer should be 0.22.
Interesting.
Oh, that's because I didn't have the actual error function. I have a multiple of the error function. Because the error function has a square root of 2 pi in it. So what if I multiply that by a square root of 2 pi? I think that's... No, that's not it either. Maybe I should have square root of pi. No, that's not it either. Okay. Anyway, we don't actually have the error function. We have an approximation of it. Just to double check that. What we were doing, we were doing an integral.
Sorry.
Yeah, we're going to start chapter 11 now.
Did we go 3?
E raised to the negative x.
So on the one thing when you check your error, how come you only go to the 2 terms?
Oh, we have 1/2 the square root of pi is what we're off by. Say it again. Why do they only go to 2 terms for what?
When you plug in 0.2, why do you only use like the first 2 terms of the power series?
Because we decided to use the Taylor polynomial of degree 3. That's what
So-
T3 means.
Uh,
So this right here is T3.
Oh, so we wrote that down earlier?
Yeah. Remember, at first I wanted to go T10.
And we were like, how about
Yeah.
not?
That was back here. Where's that? Right here. I wanted to do T10, but instead that was too complicated, so I decided to knock it down and do the 3rd degree Taylor polynomial.
Oh, so is that just 2?
So in this case, it's 2 terms because the second term has 3rd degree.
Oh, okay. So what if you wanted to go to 4th though? There's no 4th.
There is no 4, so I have to settle for T3 or T5.
Oh, okay. Alright.
Yeah.
That makes sense. I just wasn't sure because I thought it'd be like you would have to write out 3 terms, but it's just because the power was let's see.
All right. So, you guys remember trigonometry much?
It's been a few years.
We're going to review trigonometry.
I
I'm going to
enjoy
stop
trig.
this broadcast and start a new one.
But I'm sure it could pop into memory. Do you like how I wrote chapter 11?
I really like that.
Thank you.
Are we actually going to review trig, or are you going to do stupid crap at trig?
I'm going to do cute crap.